All right. Now we talked about electric fields last time, and we talked only about an electric field that was created by a single charge, single stationary charge. We're going to dig into some more complex electrical fields. What happens when I have multiple charges? Fun happens. That's what that's what happens. All right. So if we have more than one charge in the field, we can find the electrical field by summing the total forces on our charge. In other words, I've got two charges here, right? And I'm going to drop a third charge at P. Okay, a little q here. I want to know what the force on that charge is. It's going to be the sum of the force created by this interaction between these two and the force created by this interaction. So we're basically just going to sum all of the individual interactions between our point charge that we're dropping into this field and the two stationary charges here. So we can see that if I put my point charge right here, Q1, let's say that my point charge is positive, Q1 is going to put a force on it that points in this direction, in the direction of E1. Q2 is going to put a smaller force on it. Notice the smaller arrow here, okay? But it's going to be in this direction. It's going to be directly away from Q2, okay? And then we have to do some vector addition, which I know you all love. So I'm going to take this little E2 and I'm going to add it to E1, right? I put it end to end, and I get this large vector E. So E here is just the sum of E1 and E2, which are the forces created by those two charges, Q1 and Q2. That's how this whole thing is. It looks really complicated, but that's how we can make a really complex electrical field map. You'll notice that this line is tangent to this curved line, which is to say that at this point, the force is going to be right along that curved line. If I put the point here, my force line would be in that direction, right? If I put the point here, my force line would be in that direction. And it's always going to be tangent to those force lines. Now, we could make the same calculation for any point in the whole field. Um, and you get something like this image over here. Okay, so we have Q1 and Q2. And the way we draw this image is really just figuring out at every point how does the Coulomb force interact with this point from Q1 here and Q2 there. And that allows us to fill up the whole field, and we get a nice big electric field like that. Now you look at this field and you think, okay, well, what shape is that hill? What does this look like if we think of that as a topography? Well, we're kind of going downhill anywhere the arrows are pointing, right? So it looks like a kind of mound that everything is sloping away from. The interesting place is here in the middle, because these, if we drew those arrows, we could draw them closer there, and they kind of head in this direction and then fall off to either side. And this makes what's called a saddle point. And so our hill looks something like this, right? A positive charge here might go down here, but then it's going to eventually slide off the side. This would actually sort of slope out more gradually if it were really representing this hill here, but it looks something like this. And that's why in a case like this, any positive charge that's very far away is going to move away from these two positive charges. The interesting place is here in the middle, where it's going to move towards one positive charge because it's closer to this one. So the force right here is going to be more rightward than leftward created by that charge, and so it's going to kind of roll down the hill and fall off the saddle. Now, once we have that set up, we have this electric field map. We can then also draw equipotential lines for it. And so here's a negative and negative. This looks just like the other one, except our field lines are going the opposite direction. And at all of these points, we have sort of that equal elevation, just like our topographical field map. And so they're going to roll. They're going to roll towards those negative charges. A couple of things to notice about these fields. Here's another field with a positive and a negative charge in it. The arrows always point in the direction a positive charge would move. So make sure you're thinking about what kind of charge you're putting into the field when you think about what direction it's going to move. More densely packed lines, both equipotential lines and the force lines too, imply a stronger electric field. Okay, so as we spread out here and those force lines get smaller, get farther away, that means that that field isn't as strong there. Okay, and so the forces are going to be smaller. The forces right in here are going to be very strong. Field lines can never cross each other, and that's because at any given point, there can only be one way that the force is acting. And so if the force lines were crossing, it would suggest that there were two different directions that a particle might move, but it never does that. It always goes in a predetermined direction. And then field lines and equipotential lines are always perpendicular. And I think that's